Hello everybody, my name is Sasha, and today we're going to be making a video demonstration on the principles of angular momentum. I hope you enjoy the video.
Hello, I'm Charles. I'll be working with Sasha today. In this demonstration, I will hold my arms out with these dumbbells like this on top of this spinning bar stool. I will then spin myself around and pick up my feet so that I'm no longer exerting any kind of external force to change my rate of spin. I will then move these dumbbells in towards my chest, predict what will happen to my rate of spin.
Okay, so what was going on in that demonstration? So initially Charles had his arms extended outwards, and he was spinning with some initial angular velocity. Now we're assuming the bar stool is frictionless, so he would keep on spinning like that forever. Now we're also assuming his hands are massless, so we're compensating that with heavy dumbbells and on either side of his arm, and then we have this situation. Now, he's spinning in the counterclockwise direction, which means the angular momentum is pointing up in the z direction. So let me explain what that means. So, using the formula for angular momentum, it is moment of inertia times angular velocity. Now, this is what it was initially for Charles. Now, what is Charles's initial angular? What is his initial moment of inertia? It's this right over here. So it's equal to his body's moment of inertia plus. Now, since we're assuming his arms are massless and we're treating the dumbbells as point particles, which is a pretty good approximation, we can say that it is 2 times m and then r1 squared, and that's what happens. Now, as you can, and then as you saw, he drew in his hands towards his body, and then he sped up, and now he has a new angular velocity and a new angular momentum. So what is that equation? So this is it. Same as above, but this time the difference is that he has a new angular velocity and he also has a new moment of inertia, which is this right over here. Notice how the r's changed because okay, so how did this happen? So in this system, the net external torque is 0. Since we are assuming the bar stool is frictionless, there are no other net external torques acting on the system. And this is what results. And now the sum of all torques is equal to the rate of change of momentum, angular momentum. And then because the rate of change of momentum is equal to 0, L is constant. And what does that mean? L1 is equal to L2. And this is really important. This is the conservation, over here is the conservation of angular momentum. And now let's write that out in equation form. I1 omega 1 equals I2 omega 2. Okay, so we have I1 I plus 2 m r1 squared omega 1 is equal to I plus 2mr2 squared omega 2. Now, they look really, really similar. I'm now going to make a ratio. We're going to see why his angular momentum and is conserved, but his angular velocity increases when he puts his hands towards his body. We're going to explain that with this nice ratio over here. So I'm going to take omega 1 over omega 2 is equal to I plus 2mr2 squared over I plus 2mr1 squared. Now, this is an important ratio. So what can we see from here? So initially he had his arms extended, and then he drew his arms closer together. So what does this mean? What this means over here is that the denominator is larger than the numerator, right? This denominator is much larger than the numerator. Therefore, the angular momentum and the angular velocity is greater in the final position than it was initially. So as we can see, because R2 is much less than R1, therefore we can see from this ratio over here that omega 1 is less than omega 2. You can see and then what you can also see is that he initially had his arms, after he had his arms initially extended in, he extended them outwards, and then he slowed down again. And then he put them back in, and then he sped up. And that's all due to the principle of conservation of momentum. Right over here. Thank you so much for watching, and see you next time.